Good day, students. This is our online lecture on electromagnetism 2. This video lecture will be divided into small videos, around 15 to 20 minutes, not more than that. Each video will be followed up by a series of questions with solutions provided. Your goal is to go through the lecture, go through the video material, and then try the questions themselves and then look at the solutions. So in today's lecture, what we're going to cover are, we're going to cover the concept of electromotive force, connection of resistors in series and in parallel, magnetic phenomena, and the Faraday's law. Let's start our lecture by revising some of the material from the previous lecture. Let's say that we have a piece of wire such that this side of the wire is at a higher potential. So let's call it V1, and this side of the wire is at a lower potential, V2. So we're going to say that V1 is higher than V2. Now we know that the electric field is pointing from a higher potential to a lower potential. So the electric field here will be pointing from here, to the right. So this is the direction of the electric field. In the wire, we have free electrons, which are negatively charged particles, and because of these free electrons, and because of the electric field, these free electrons are moving in the opposite direction to the electric field. And this has to do with their sign. Their sign is negative, so the direction is opposite to the direction of the field. In this model, thinking of the motion of electrons is not very convenient because the direction of the motion of electrons is opposite to the direction of the electric field. Instead of thinking of electrons, let's think about positive particles which are moving along the direction of the electric field. So, instead of thinking of the electrons now, I will be thinking of positive particles which are moving in the direction of the field. So I am changing the sign of the particles, and I'm changing the direction of motion of these particles. So they're moving along the electric field. A very good analogy in relation to this electric current is the analogy with water. Think of current as water, electric current as a water, and then the wire as a pipe in which the water flows. So we know that if the water pipe is inclined, then the water flows naturally from a higher point to a lower point. So the water will just flow from the hill to the valley. So same thing can be done here. We can think of this as water which is going from a higher potential to a lower potential. So the water, that is the current, is flowing naturally from a higher potential to a lower potential. However, then the question is, well, if the current naturally flows from a higher potential to a lower potential, just like the water, then how do we bring the water back to the higher point? How do we get this water from the valley to the hill? How do we get this electric current from a lower potential back to the higher potential so that it can flow down back? And to do that, we need the so-called electromotive force. EMF is an abbreviation and it stands for electromotive force. Even though there is a word force in this abbreviation, it is not a force in a real sense. Electromotive force, in our analogy, can be thought of as a pump. Imagine you have a pump which pumps the water from the valley to the hill, and then once the water is on the hill, it can just flow down. So this is exactly what EMF is doing. The EMF is taking these positive charges from a lower potential and brings them back to the higher potential so that the current can flow back. And so this is what EMF is doing. Now, electromotive force is an agent of a non-electric nature. So it can be, for example, of a chemical nature. It could be of mechanical nature. You can simply take your hand and, I mean, we can imagine like as if you're taking these charges and bringing them back here. So you're doing this mechanical work by getting these charges from here to here, from a lower potential to a higher potential. In a battery, a regular battery that you have in your cell phones, this is being done through a chemical process. So in this chemical process, inside the battery, the charges are being moved from a lower potential to a higher potential, just like a pump. So this is what electromotive force is doing. Now, how do we represent an electromotive force in a circuit? In a circuit, an electromotive force is labeled with this sign, okay, with a larger bar standing for a positive side and the smaller bar standing for the negative side. And the symbol for it is big E. Now, we said that the electromotive force is responsible for moving these charges from a lower potential to a higher potential. So there is some kind of force which is actually moving the charges from the lower to a higher potential. So this force is doing work. And work, as we know, is measured in energy. Electromotive force is the amount of work done by that agent per unit charge. So you can think of this as simply as the amount of work done per unit charge in moving these positive charges from a lower potential to a higher potential. Let's look at a simple circuit. In this simple circuit, I have three elements. I have the EMF itself. I have the so-called load resistance. Load resistance is anything that you need to power with this EMF. It could be your bulb, it could be a motor, or it could be any other device that requires electric energy. So, load resistance. However, there is also this small element, which is also a resistance, but the so-called internal resistance. This internal resistance is the part of a battery. And I'm going to label the battery with this dashed line. So everything that's inside this dashed line is a battery. So what do we have in that dashed line? We have the EMF itself, this agent, which is the pump. And we have the internal resistance. So what is this internal resistance? This internal resistance is the so-called parasitic resistance. It is the resistance in the battery itself. Okay? So the battery itself has its own small resistance. Sometimes it's negligible and we can ignore it. But in general, in real life, resistance is the internal resistance is non-zero. In an ideal case, of course, when the EMF is thought to be as an ideal device, then the internal resistance would be equal to zero. Now, in this simple circuit, we can label 2 points. We can label point 1 and point 2. Now, these 2 points, which are just outside the battery, are the terminals of the battery. So these are terminals of the battery. And using the same word, we can think of the so-called terminal voltage, the voltage difference between these 2 points. The voltage difference between these 2 points. We know this side is positive, this side is negative, so V1 is at a higher potential than V2. Which means that potential difference, which is V1 minus V2, this potential difference is the terminal voltage. Why do we call it terminal? Well, because it's the voltage across the 2 terminals of the battery. So this is the terminal voltage. If this is the terminal voltage here, then the same voltage, the voltage difference between these 2 points, the same voltage difference is between these 2 points. Why? Because these wires, they don't have any resistance to them. So the voltage difference between these 2 points is the same as the voltage difference between these 2 points. Which means that according to the Ohm's law, we can calculate what is the current that is flowing in this resistor. The current that's flowing in the resistor, according to the Ohm's law, is then equal to this terminal voltage, and I'm going to use a subscript T to specify that it's a terminal voltage, over the resistance R. Now let's think about this current. As the current starts from here, it flows down, and we know that it's going from a higher potential to a lower potential. So now our voltage is decreasing as we're moving here. Okay? Then we come to this point, and we move down in voltage even further. Okay, so which means that we can now say that when we bypass this EMF, we can say that the EMF is equal to the voltage difference between these 2 points, which is this voltage difference, plus this drop in the internal resistance, which is I